alkynes, right? So if anyone remembers back at the very beginning, what is an alkyne, or what is that? It's a triple bond, right? So specifically, it's a carbon-carbon triple bond. And one of the most basic alkynes we'll see quite a bit. It's this C2H2, right? So this guy is the most basic of the alkynes. This is what we call acetylene. So this is acetylene, which is confusing, right? Because it's an alkyne and it ends in an ene. I don't know about the history behind that, why those are like that, but acetylene is one of the most basic of our alkynes, okay? All right, so let's talk a little bit about what makes up a carbon-carbon triple bond, right? So if we remember back in the first semester of general chemistry, what is the molecular geometry about that carbon-carbon triple bond?
Then it can't move, it can't rotate.
Can't rotate, right, because we have pi bonds, but specifically that overall structure of that molecule, what is the molecular geometry, or what are the bond angles for these guys right here? Angles.
It's straight.
It's straight, right?
Linear.
It's straight, or it's linear.
Is it 180? Sorry.
Right. And so the bond angles here are 180 degrees. Now that 180 degree bond angle comes from the fact that we're using a specific type of hybrid orbital. So what type of hybrid orbitals are these carbons using to form these bonds, right?
SP.
Right, so these guys were sp hybridized. So sp hybridized, how many p orbitals did that leave behind that were unhybridized?
2.
2, right? So each carbon has an sp hybridized orbital as well as two p orbitals that are unhybridized but still capable of bonding, okay? So we got a couple of different bonds out of these hybrid orbitals and these unhybrid orbitals, right? So with the sp, these guys combined in what we called a head-on fashion, right? So we had orbital overlap in a head-on fashion with our sp hybrid orbitals. What type of bond did that produce as a result? If we have head-on orbital overlap, type of bond specifically, is it sigma or pi?
It's sigma.
Sigma bonds, right? So sigma bonds form via this head-on orbital overlap. So this is our sigma bond. And again, this is due to those sp hybrid orbitals overlapping, right? Again, they have unpaired electrons. When they overlap, they spin pair. We get a bond as a result. Again, this head-on orbital overlap occurs along this internuclear axis, okay? Now, what about the unhybridized p orbitals? We had 2 of them for each of our carbons, right? Are those going to overlap in a head-on fashion, or are they going to overlap instead in a side-on fashion?
Side to
The
side.
side-side, right? So these guys overlapped in this side-to-side fashion, right? And we had 2 of those sets that did the same thing. So what type of bonds are those guys producing?
Pi bonds.
These are pi bonds, and specifically, it is 2 pi bonds, okay? So, carbon-carbon triple bonds, all of these alkynes that we're going to be dealing with come about because of the head-on orbital overlap that produces the sigma bond, and then the 2 side-on orbital overlaps that produces the 2 pi bonds, okay? Okay, so a couple other things to talk about, and this is kind of a refresher. So if we compared something like ethane, so ethane is our alkane. This is just all of our carbon-hydrogen single bonds. So this guy is ethane. We compared that to ethylene, which is our carbon-carbon double bond. So this guy here is ethylene. And if we compare that to acetylene, who do you think has the shorter bond angles?
Ethylene.
So shorter bond angles, right? So that's going to be our acetylene, but what was the rationale behind this? Shorter bond lengths. Did I say angles? I meant lengths. Yeah. So shorter bond lengths. My bad. So what was the rationale? How could we explain that away? The fact that acetylene was a little bit shorter of a bond than ethylene, which is a little bit shorter of a bond than ethane. So this guy was about 100 or 1.2 angstroms, whereas this guy's about 1.35 angstroms, whereas this guy's about 1.53 angstroms. And I'm measuring this bond length between the two carbons. So how can we explain that? Or how did we explain that? Why this guy has so much shorter of bonds than this guy, who has shorter bonds than this guy?
Is it the overlapping?
It has to do with the orbitals. It's specifically what type of orbitals are forming the sigma bonds for each one, right? So for acetylene, we already talked about these carbons are using sp hybrid orbitals. What are the carbons in ethylene using? sp2, right? So this is sp2 hybrid orbitals versus our ethane. What type of orbitals are those guys using? sp3. Now this goes back to this idea behind S character, right? So for sp hybrid orbitals, what percentage S character are these orbitals? 25%. So again, there are 4 of them, and one of them is coming from the S orbital. So 1/4 of those guys is going to be the S character. That's where we get the 25%. Whereas ethylene, or any type of sp2 hybrid orbitals, is about 30% S character. And then for sp, it's about 50% S character. So who overall is closer to the nucleus? The S orbitals, which are these nice spherically symmetric, or the P orbitals?
Wait, say that again?
Who's closer to the nucleus, S or P? S orbitals are closer, right? So the more S character we have, the closer that we're getting these guys with respect to one another, the overall shorter the bond angle, or bond length. Length, we're talking about links, sorry. Okay, so again, going back to that 50% S character in acetylene, that's what's making these bond lengths between these carbon-carbons so much shorter than the ethylene versus the ethane, okay? It's the S character of the hybrid orbitals that we are using. Okay, so that's kind of like a background. What are alkynes? We're looking at carbon-carbon triple bonds. This is a new functional group, so usually the way when we introduce a new functional group, we'll talk about some specific characteristics of it. Then we'll go into nomenclature. How do we name our new functional group, okay? So next thing we're going to talk about then is how to name these guys. So we're going to follow the exact same 4 basic rules that we did for our alkanes as well as for our alkenes, okay? So the first thing we're going to do is identify the parent chain. Now, with respect to alkynes, because again, that's what we're dealing with alkynes. The parent chain is going to be the longest carbon chain that contains the carbon-carbon triple bond, okay? So it has to have the carbon-carbon triple bond. This is very similar to what we saw for alkenes, right? So the alkene, we had to have the carbon-carbon triple bond. Then we're going to identify and name the substituents. That's always the same for the most part. The only thing that also changes is we're going to number the parent and assign the locants, right? And so now what is going to happen with respect to these alkynes is that we're going to give the carbon-carbon triple bond the lowest number possible, no matter the other substituents that we have.
So we'll start from wherever the closest triple bond is?
Yeah, we're going to give, or we're going to number the chain so that the triple bond gets the lowest number possible, okay? Even if something else. So even if there was a substituent in numbering the other way, it doesn't matter, we're going to give the triple bond the lowest number. Okay, so as an example of that, we have this guy down here, right? So when I'm looking for my parent chain, I'm looking for the longest chain that has that triple bond. So if I count that, I'll find that I have let's do this guy. We have 1, 2, 3, 4, 5, 6, 7 carbons here. So what is 7? It's hept. So we'll leave this as hept because we're going to talk about what the ending is going to be. Again, though, as I go through and I number this guy, I want to make sure and give this thing the lowest number possible as opposed to giving a substituent the lowest number possible. So the incorrect version would be starting here because that would give our triple bond a 5. We actually want to start on this side so that we give our triple bond a 2, okay? So this would be the correct numbering. Again, we're going to identify the substituents. So what are the substituents off of this parent chain?
Trimethyl, 5, 6.
Right, so we've got 3 methyls, right? So all of those are methyls. These guys are all methyl. Now, the only change that's going to come in here is when we number the overall parent, okay? So we're going to go ahead and start the same. We've got a 5, 5, 6 trimethyl. So 5, 5, 6 trimethyl. But now that hept is going to change into an yne, because again, we're dealing with alkynes, right? So the ending here is going to be YNE as opposed to ENE or ANE. And to identify where this guy starts, we're going to follow the same convention that we did for alkenes. So we're going to go hept, and then we're going to say 2, and then we're going to end it in yne. Now, that seems fairly easy. I'm going to talk about what happens if we get multiple functional groups here in a second. So for right now, the only thing that changes, finding this guy, our parent chain is the longest carbon chain that contains this. When we number it, we want to give this guy the lowest number possible, and our ending is now going to be YNE as opposed to ENE or ANE, okay? Now, a couple other things with respect to these. There are a couple of common alkynes that go by their common name that'll be important to actually identify them. So acetylene is one of the big ones, right? So just the carbon-carbon triple bond, knowing that that's acetylene is important. There's also a methylacetylene, a diisopropylacetylene, and then a phenylpropylacetylene. So again, these are not the IUPAC names, they're the common names, but it'd be important to know what those are. And then other terminology that we use with respect to alkynes kind of deals with the substitution about the carbon-carbon triple bond. So for example, when we had alkenes, we talked about how substituted that carbon-carbon double bond was. Like for example, with this guy, what would be the substitution about this? Would this be mono-substituted, di-substituted? Mono, right? So this guy's a mono-substituted alkene. We have a similar type of terminology for alkynes, but now there's only like 2 possible variations of it, right? So now, for example, this guy, what would you consider that in terms of substitution about that alkyne?
A mono.
It'd be a mono-substituted alkyne. We call those instead terminal, right? Because they essentially end a molecule. And then for this guy, you would consider this like a di-substituted alkyne. This is internal because they're in the internal side of the molecule. So there's only terminal versus internal. And again, it's kind of comparing that mono versus di. Okay, so then I'm going to do a practice with respect to the nomenclature, and I'm going to let you guys name a few. But I actually want to change the one that I do. So originally I had this guy. I don't want to name that one. I instead want to do something a little different, which is this guy instead. Okay, so the reason I'm going over this is because this guy has multiple different functional groups in it, right? First off, we have a halogen, right? So in theory, this is kind of like an alkyl halide. We've talked about how to name those. It has a carbon-carbon double bond, so it's also an alkene, and then it has a carbon-carbon triple bond, so it's also an alkyne, okay? So how are we going to go about naming this?
Find the longest with the steps.
Right, so doing the steps, right? As a note, comparatively, IUPAC has kind of assigned priorities to certain functional groups, and right now, our alkenes and our alkynes are kind of equal. So alkenes and alkynes are equal, but they're all going to be greater in priority than our alkyl halides. right? So we're always usually going to name the alkyl halide as a substituent. These guys are actually going to take priority over that, okay? So the question then is, well, if we've identified the parent chain, right, again, we're going to have the longest carbon chain that has both the double and the triple bond. That's what we're looking for. So for this guy, we're looking at 1, 2, 3, 4, 5, 6, 7. So again, we're dealing with a hept here.
All right, wait a minute, no, because I thought we were supposed to have the alkene the lowest. You understand why?
Yeah, no, so I'm going to go through how we actually figure out numbering if we are competing between an alkene and an alkyne. Okay, so then the question is, well, how do we number this, right? Who are we going to give the lowest number possible to? And it's going to be either of them. You're going to number it so that whoever comes first is going to get the lowest number possible, okay? In this example, it doesn't really apply because if we start numbering over here, it's 1, 2. If we start numbering over here, it's 1, 2. So there's a tie, okay? So if there's a tie in the numbering, we give the alkene the lowest number possible. So if there's a tie, which one? Sorry.
The alkene, the double bond.
The double bond will get the lowest number if there's a tie in how we number them. So if it's a tie, the alkene gets the lowest number. Okay, so then what comes next after that? We've numbered it, right? So we have 1, 2, 3, 4, 5, 6, 7. How are we going to start assembling this?
Start adding your substituents.
So also note stereochemistry. So there's only one thing that we have to worry about in terms of stereochemistry here. It's not the alkyne, it's not the halide, it's instead the alkene. Right? So what type of options do we have in stereochemistry for the alkene? E versus Z. So for this one, how would I assign it being E versus Z?
A Z.
A Z or E.
So again, I'm going to go on this side of the double bond. Who gets number 1 priority? Bromine or the methyl?
Okay.
Bromine, because it's heavier, right? I go over to this side. We've got a hydrogen here, right? So who gets the highest priority, the hydrogen or that other carbon chain?
The carbon chain.
The other carbon chain, right? So here we have 1 and 1. They're on the same side of the double bond, so this is E versus Z. Z, okay? So we do have to worry about that. So we'll start that with a Z. Now we'll move into our substituents. We only have 1. It's bromine, right? So this is going to be 2 bromo. And then what happens? What is the parent? The parent was hept, right? So we'll move into hept. But now what we're going to do is the ene is going to come first, right? Again, we're going to specify where it's at via its locant. So this is 2. And then it's usually ene, right? So normally it's E-N-E. We're going to drop the E when we name this. So it's 2 ene, and then we specify the yne. So yne is at 5 yne.
I don't like it.
Yeah.
This is ugly. Is there like another common name that we can call that?
She told
Nope.
us it was gonna get ugly around spring break.
What,
Yes, Eric.
What if there was one where alkene and the alkyne weren't, I guess, like on like equal, I guess. Like what if it was instead it branched off right next to it and then there was the alkene and the alkyne and like
So if it was like this, right?
yeah.
And we had gone through and said, because now there's not a tie, now it's 1, 2 versus 1, 2, 3. We're going to give whoever gets the lowest number, the lowest number.
Okay.
The only reason why we had to pick between this and this is because when we started numbering, they both were at 2. So if there's a tie, then the alkene gets priority.
Okay.
I want to get rid of that, though, because I don't want to confuse people. Yeah. Yes.
so what if the lowest was the triple bond? Do we still have to worry about E or Z?
Yeah. I mean, E or Z depends on this guy. right? We have to specify, is bromine over here or is bromine over here? And that's what easy is telling you, right?
We would do that for a double bond.
We'll only do that for double bond. Triple bonds we don't care about because there is no stereochemistry there. You would also have to be concerned with a stereocenter, a chirality center. If there was one, there is not one in this molecule. You would also have to specify that in the front of the name. So this is why using this convention where we do the locant followed by the end functional group is helpful in this whenever we have to deal with multiple functional groups in a molecule. Okay, so let's do a practice problem. Let's do a few together, or, obviously on your own, and then we'll go over them. I want to again remove one of these though to give you a little bit harder of one so that you can apply what I just talked about. So let's ignore this guy, and instead I want you to name this guy, if that's clear-ish. Okay, so we had gone over these in class, but I'll go ahead and answer. I'm coming up with the correct IUPAC name for the following compounds. Okay, so again, with respect to alkenes, we're looking for the longest carbon chain that contains the carbon-carbon triple bond. And if we start over here with A, we'll find that we've got our carbon-carbon triple bond here. Again, we're looking for the longest chain. So for this guy, I've got 1, 2, 3, 4, 5. If I keep going out here, I'll get 6, 7, 8. That would give me an octane. But I think the longest chain here actually was 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9, we know that the base here, or the prefix, is non. And because, again, this is a carbon-carbon triple bond, we're going to end this in non-9 at this point. Okay, so if this is our parent chain, then we're looking for the substituents that come off of it. So we have a methyl group here, methyl, and then we have a meth-eth propyl group over here. And so now all we need to worry about is numbering it. So we want to number it so that the carbon-carbon triple bond gets the lowest number possible. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So now we can start assembling this. We had a methyl, we had a propyl. So M comes before P. So we have a 7 methyl. We have an 8 propyl. And then we're going to move in directly to, maybe I shouldn't do that there. Okay. We'll go over to this side. So we had a 7 methyl. Why did I say 8? I don't know. So 7 methyl. Then we had a 5, propyl. But again, we want to go ahead and move into the parent chain. So this is non, but we need to specify where the triple bond is. The triple bond starts at the 1 carbon, so this is non-1-ine. And again, another way that you could have done this, which is technically correct, but not preferred, is the same 7 methyl, 5 propyl, and then 1 non-ine. Okay, so then we'll move on to number C. Just as a note here, this, because the molecule ends in a carbon-carbon triple bond, this would be what we consider a terminal alkyne. Just to review some of the ways that we can classify these guys. All right, so number C, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. I think that's the longest chain that we're going to find here. So again, this guy's also non-ine. Again, we want to number this so that the carbon-carbon triple bond gets the lowest number possible. If we start over here, that'll give it 3 as opposed to 1, 2, 3, 4, 5, 6 on the other side. So we'll start at the bottom. This is 4, 5, 6, 7, 8, 9. And then for our substituents, we have a 1. So we have 1 methyl here, we have a methyl, and then we have an ethyl group. So this guy's going to be a methyl and an ethyl. So now we're ready to assemble the name. So ethyl comes first, so this would be a, let me change colors, this would be a 5 ethyl, and then a 7 methyl. And again, we'll move into the parent at this point. So this is non, and now to specify where that carbon-carbon triple bond starts, we'll say 3-ine. What's great about these alkynes is that you don't have to worry about stereochemistry. So there's no E, there's no Z. As long as there's not a chiral center, then you don't really have to worry about anything. Second, again, as this one was a terminal alkyne, this is a internal alkyne, because again, the carbon-carbon triple bond does not terminate the molecule, so this is an internal alkyne. Great. Yep, spelling is great. Alkyne. Okay, so those are kind of the easier ones. All they have is the triple bond, so it's just an alkyne. Over here, I did give you guys this one to be a little bit more difficult. So this contains both a double bond and a triple bond. Okay, so in the practice problem I had given you, we had gone over one of these that had both a carbon-carbon double bond and a triple bond. And so we talked about, we're going to have these priorities with respect to these functional groups. And we talked about the fact that alkenes, or our double bonds, are equal in priority to our alkynes. So what that means is when we're looking for our parent and we have both of these groups, we're looking for the carbon chain that has the longest carbon chain that has both of them. For this one, that's not an issue because there aren't really any substituents. Here we have 1, 2, 3, 4, 5, 6, 7. So the parent here is going to be heptyne, or hept, we'll call this right now because 7 carbons. When we're numbering this, we have to specify that. And so how we number this is we're going to give, we're going to number it in a way to give the lowest number possible to whoever comes first, right? So if I started on the left-hand side, the carbon-carbon triple bond would get 1. Or if I started on the right-hand side, the first functional group that we would come to is at carbon 2, right? So we want to number this to give whoever comes first the lowest number possible. So that would be starting on the double bond side. So we have 1, and then 2, 3, 4, 5, 6, 7. Again, there is no there's no substituents here, so we don't have to worry about it. All we have to do is specify where each thing is at. And we don't have to worry about stereochemistry either, because at the end of our alkene is a hydrogen and a hydrogen. And again, we don't have any cis trans or EZ whenever we have the same group attached to the same carbon. So we don't have to worry about any of that. So instead, now we're going to start to go ahead and organize this. There's no substituents, so this is just hept. And then we specify where the double bond is, 2, ene, and then the triple bond is, oh, it's not 2, pardon me. Man, organic chemistry. Hept 1 ene, and then this is 5 ine. So hept 1 ene, 5 ine. And again, when we do have these multiple or multiple functional groups, both the ene and the ine, this is when putting the number in front of the ending becomes extremely helpful, as opposed to putting the number out in front like we did over here before the parent. Okay, so hopefully that made sense. We all got the correct answers on those. Into any type of reactions. So as a reminder, we talked about acid-base chemistry back in the first semester, right? And we had talked about how to predict whether or not something was going to be relatively more or less acidic, right? So first off, there's the quantitative measure, which is a pKa value, right? So we know pKa's, we can essentially say, oh, who's more acidic? The larger the pKa, what can you tell me about that molecule? Larger pKa,
It's more basic.
right, it's going to be less acidic, okay? So we should be able to note that as we go from ethane to ethylene to acetylene, what happens to the pKa values? What happens to the acidity of these molecules?
It decreases.
It decreases, so who's going to be the most acidic here?
The acetylene.
The acetylene, right? So acetylene is much more acidic than ethylene or ethane. What was the rationale behind that?
The acid thing.
So remember, how did we determine kind of the relative acidity of things? We always looked at the stability of the conjugate base. So the conjugate base of acetylene is something called the acetylide ion, and we're going to again see this again. So I want to define this as acetylide. The conjugate base of ethylene, I don't actually really know the name, doesn't matter. But again, we have the negative charge here. And then the conjugate base of ethane, we would have the negative charge on this carbon, hydrogen, hydrogen, carbon. Right, so now, how do we determine who is more stable?
Hold on one second, we're still ready.
So remember AREO?
Yes.
We looked at the stability of these conjugate bases, right? We're looking at the negative charge. What did A stand for?
Atom.
Atom, right? So what, for all of these guys, what atom is the negative charge on? It's on carbon, right? So atom isn't going to necessarily tell us who's more stable here. What about resonance? What about R?
They're all the same.
So resonance, are there any resonance for any of these conjugate bases? No, right? What about I? What was I?
Induction.
Induction. Are there any electron withdrawing groups on any of these guys?
No,
No, so it's all the same. And then what was O? Orbitals, right? Again, what are we looking at? What type of orbital is the negative charge on the acetylide ion?
SP.
SP hybrid orbitals, right? So this is SP. This guy is SP2, and this guy is SP3. Which one is going to be more stable?
No, SP.
Right, so we want to get this negative charge as close to the nucleus as possible because that's where the protons are. That's what's going to stabilize it. So the orbital that gets those closer to the nucleus is going to be the more stable orbital. And again, because SP is 50% S character, this guy's going to get things closer to the nucleus, so this was the most stable. What? Sorry.
No,
Okay. So because of that, because the acetylide ion is the most stable comparatively, acetylene is the most acidic. And actually, comparatively, acetylene and any type of terminal alkyne is going to be fairly acidic overall, comparatively to like a lot of the other organic molecules that we use. Okay, so again, acetylene is fairly acidic. Now the question is, what the things are going to deprotonate acetylene? Okay, so meaning deprotonate, taking off a proton, making this acetylide ion. So again, we utilize that AREO concept to explain which position of equilibrium an acid-base reaction is going to favor, right? So in terms of AREO, when we had an acid-base reaction, equilibrium was always going to favor the side that made the weaker conjugate base or the more stable conjugate base, right? And so one of the exceptions that we had talked about in the first semester was this acetylide versus amide. So again, when we're trying to compare this position of equilibrium, whether or not products are favored or reactants are favored, we're going to compare the two bases, right? And if we used AREO as is, what would we start at? What is atom? So atom for this NH2 molecule, what atom is this negative charge on? It's nitrogen. Whereas for carbon, or for acetylide, what is the atom that the negative charge is on? Carbon. So just stopping there, who would you predict would be the more stable conjugate base? You would think it'd be the nitrogen because, again, it's more electronegative than carbon. It lies farther to the right. This was the one exception to our rule, okay? Because our acetylide uses this sp hybrid orbitals, this actually ended up being the more stable base comparatively, even though AREO wouldn't tell us that. And so equilibrium favored the production of the products, favored the production of this acetylide or deprotonated acetylate, okay? So one base that can do this is this guy, NH2. What do we call this? NH2 minus. This is the amide, right? We're going to see this guy come up a lot. Again, it's not just in the form of the base, in the form of amide. It's always going to be paired with a counter ion. So this is usually in the form of sodium amide. This is going to be capable of deprotonating acetylene, okay? Now, what about something like hydroxide, who's our kind of standard common base? Again, if we utilize areo here, the atom for hydroxide, where the negative charge is at, is oxygen, whereas again for acetylide, the atom is carbon. Can we use the atom to determine who's going to be more stable? Yes, for this one, right? We can't do it for amide, we can't do it for nitrogen, but we can use atom here. Oxygen is always going to be more stable. So this guy is the more stable base, or another way to write that would be the weaker base. And so in this reaction, it's actually going to be reactants that are favored, right? So reactants are going to predominate at equilibrium, meaning that hydroxide is not strong enough of a base to make this guy, right? Hydroxide is not going to be strong enough of a base to deprotonate acetylene. So if we want to deprotonate acetylene, we can't use hydroxide. Other forms of very similar compounds are going to be our methoxide, all these deprotonated alcohols, or ethoxide. None of these are going to be capable of deprotonating acetylene. The only things that will be capable are things like our sodium amide, as well as hydride, as well as any type of deprotonated carbon-containing compound. So if we want to deprotonate acetylene, we have to use a stronger base than hydroxide or methoxide or ethoxide. It has to be amide, it has to be hydride, something like that. No T-bute, no Naomi, nothing like that.
Can you draw acetylene?
Acetylene, yeah,
Yeah.
it's here.
Okay, so the summary of this slide is just saying that all the oxides.
All the oxides are not strong enough to deprotonate acetylene. If we want to deprotonate it, we have to use a stronger base, and those stronger bases are sodium amide or hydride or any type of deprotonated alkane. Okay, so now the question is, well, how do we make an alkyne? So to kind of answer that, first off, how do we make an alkene? What were we usually starting with?
An alcohol halide.
So what type of reaction would have taken something and would have produced an alkene or carbon-carbon double bond as a product?
Elimination.
Elimination reactions, right? So we had a main one, which was E2. What was going to be the type of starting material we needed for E2? An alkyl halide, right? So we needed to make an alkene, an alkyl halide. That guy in the presence of a strong base, so the strong base was anything like Naomi, was going to produce our alkene. So now we're going to see the exact same thing to produce an alkyne, except now we need two halogens on the molecule. Okay, so we have to start with a dihalide, and there are going to be two forms of this. This guy's then going to undergo two subsequent elimination reactions, right? So the first elimination would produce the alkene. So for this guy, we would be left with a carbon-carbon with R and a bromine, and then R and a hydrogen. This is one elimination. In a subsequent elimination, we've got another leaving group, we've got another proton. We would end up with our final alkyne product.
So you cannot make an alkyne in a controlled fashion.
So it's two elimination reactions, right? Now, as a note here, there are two different types of dihalides that we can use. So the dihalide where we have the bromine on the same carbon, this guy's called a geminal dihalide. We can also have starting material as a vicinal dihalide. So a vicinal dihalide has the leaving group, or the bromine, on both of the carbons. So geminal gives us bromine on the same exact carbon. We can again do a double elimination here to get the alkyne. We could also start with a vicinal dihalide, where the bromine's on the opposite carbons, right? This can also lead us to our alkyne.
Quicker or sooner?
What?
Quicker? Or requires both eliminations?
Both of them require two elimination reactions. We also still have to have 2 hydrogens that we can remove.
So you're gonna have a carbocation.
So no, we're not going to go over the mechanism for this guy,
Okay.
but we do need to note, right, for our elimination up here, to get the alkene, we could use things like Naomi, right? In theory, to go from here to our first part, we could use things like Naomi, but then we'd have to like purify it, remove it, do more stuff with it. So we need a stronger base than things like Naomi or ethoxide or any of those guys. So what base did I just introduce to you that's capable of producing, or at least deprotonating, an alkyne? Yeah, so the Na, so the sodium amide. So to make an alkyne, we're going to have to start with a dihalide. Then we're going to need 2 equivalents of our sodium amide in the presence of ammonia. To drive this reaction to completion, though, we go ahead and introduce a 3rd equivalent of our sodium amide to produce our acetylene or our alkynide ion, okay? So the way that we essentially write this in our overall reaction is we'll say excess NaNH2, and again, this is in ammonia. So this is going to drive this to the production of the alkynide ion, which is essentially driving this overall reaction. We can't end here, though, right? So what should we do? We need to protonate this at the end. What could we add that would protonate this alkynide ion? We need an acid. Does it need to be that strong, though? No.
Charge.
Right, so water is strong enough of an acid to protonate this alkynide to produce our overall final alkyne product, okay? So this occurs in 2 separate steps. First off, we do the elimination, which brings us to here, and then in the second step, we add water to protonate this and give us our alkyne. So again, with this reaction, the question is, how do we prepare this carbon-carbon triple bond? This is it. You have to start with a dihalide, right? You're going to put it in the presence of excess sodium amide and ammonia. That's going to give us here. In the second step, we're going to add water to protonate it and end up with our carbon-carbon triple bond. Yes?
Will you please upload this video? I'm struggling, like, just a lot. So, the NH2 acts as an acid to
It's a base.
As a base.
It's a base. So again, we talked about this guy being strong enough of a base, sodium amide, to deprotonate acetylene. It's also going to be strong enough of a base to take this dihalide and to produce the carbon-carbon triple bond in the first place. But again, the way that we drive this reaction to completion is we put in this excess, right? So we put in a bunch of sodium amide to get to that final alkynide ion. At the end, though, we still have to protonate it, so we add water to do that. So as an example, you would be given something like this, where I give you the structure of a dihalide, and I tell you this is in the presence of excess sodium amide in ammonia, and in the second step, water. What am I going to produce? What is my product at the end of this reaction?
You're gonna have an alkyne.
I'm going to have an alkyne. Specifically, though, note that
Terminal.
it's going to be a terminal alkyne, right? Because again, our dihalide is on this last carbon. The protons still have to be removed from the adjacent carbon, from that beta position, just like the original elimination reaction. So if the protons are coming here, the triple bond is forming between these 2 carbons, okay? So I would then write that our product over here is just, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 goes up. So note overall that with our alkynes, we have to maintain linearity when we draw our bond line structures. We have 1, 2, 3, 4, 5 carbons. The triple bond is forming between these two guys, so I have to go up with that. Does that make sense?
Oh, yes.
So again, same thing. We have an alpha carbon. We're going to be doing this elimination between our alpha and beta positions. That beta position still has to have protons. That ended up being this carbon here, but that could be different. So again, you're looking for a triple bond forming between alpha and beta. Beta has to have 2 protons to eliminate. All right, so let's try that. We have a question where I want to know what is the product of this reaction. I give you a dihalide. This is a geminal dihalide because the 2 bromines are on the same carbon. This is in the presence of excess sodium amide. And then in the second step, we've added water to protonate whatever the final product is. Okay, so again, we dealt with this when we talked about the preparation of alkynes. And so one way to prepare them is to have a dihalide, is to react that in the presence of a very strong base, because again, we need a base that's stronger than an alkene, essentially, to be able to protonate an alkene. And so sodium amide is the base that's going to help us do that, right? So anytime you see excess, that means we have more than however many equivalents we need of it. This is sodium amide in the presence of liquid ammonia. That's the first step. And so if we did that, again, we have an alpha carbon here, and we're going to form a carbon-carbon triple bond. As long as we have 2 of these guys, we've got excess of this, and we have 2 protons to go ahead and remove as well. So that's really important in this. So at this point in time, if this is our alpha position, then we have a beta position here, and we have a beta position here. So the reason we know that the triple bond is going to form between these 2, and I don't like that, I wanted that to be a highlighter, is because there are no protons to deprotonate, and that's an important step in the elimination reaction, right? So what we're going to end up with is we're going to end up with a carbon-carbon triple bond here, right? And that's the first step, right? But because it's excess, and because sodium amide is a stronger base than this terminal alkyne that we're producing, we're going to end up with the alkynide ion, right? So what I'll show is the actual product of this first reaction. So this is 4 carbons, so we'll end up with a 1, 2, and then in between 3 and 4, we're going to get a triple bond. Except, again, I won't want to go up here because we know that triple bonds are linear. So I would draw this like this. At the 2 position, we still have these 2 other methyl groups. So just the first step, because it's excess, that's actually going to deprotonate that terminal alkyne, and we'd end up with the alkynide ion. This, again, is the alkynide ion. I guess it'd be probably like butanide, that's it. No, I made that up, so don't ignore that entirely. Anyway, so we end up with the alkynide ion. Again, we can't end up like that. Nobody really wants to end up like that if we want an alkyne. So to protonate this, we need to add an acid that is stronger than the alkene, and that acid ends up just being water, right? Water's not super acidic in our terms, but comparatively to an alkene, it is. So this was the first step, would produce this guy. We have to include water in a second step so that we end up with our protonated terminal alkyne. And so this would be our final product here. So again, anytime you want to make a carbon-carbon triple bond, you need a strong base, so excess sodium amide. You need water in the second step, and you need a dihalide to actually undergo those 2 separate elimination reactions. Alkenes. So remember all the reactions that we had for alkenes? What do we call those reactions? So we had an alkene, and we did something, we reacted it with something, and it made something else. What were all those reactions called? Addition reactions, right? How many addition reactions do we have for our alkenes?
7.
a bunch, right? So we had hydrohalogenation, we had hydration, we had all of these. Same thing. We're going to have pretty much all of the same ones, except we're going to be doing it with an alkyne instead, okay? So the first one we talk about is actually that catalytic hydrogenation, right? So for example, if I had an alkene and I wanted to produce an alkane from that, how was I going to do that? What type of reaction is this? It's addition, but what are we adding to that double bond?
For the first one?
For this guy up here that I just drew. Taking an alkene and turning it into an alkane.
Oh, hydrogenation.
Hydrogenation, right? How do we do that? What were the reagents that got us there?
Hydrogen.
Hydrogen, but it also had to be in the presence of what? A catalyst, right? It was catalytic hydrogenation. Good catalyst for that is platinum metal, okay? Now, in terms of stereochemistry for this reaction, how did that hydrogen add? Was it in a syn or an anti-fashion? It was in a syn fashion, right? Because we had our platinum metal, and we had our hydrogens essentially bound to that platinum metal, and our alkene had to come over the top, and those hydrogens had to get added to the same side, okay? So overall, turning an alkene into an alkane, we call that catalytic hydrogenation, but it's also a reduction reaction. We're reducing an alkene to an alkane anytime we add hydrogen. Okay, so same exact thing is going to happen with our alkynes now. So if we take an alkyne, a carbon-carbon triple bond, and we put it in the presence of platinum metal, what we're going to get is or hydrogen in platinum metal. What we're going to get is complete reduction to the alkane. Okay, so we have an alkyne, and we're going to get complete reduction to the alkane. It's very similar in the way this adds, right? So it's going to be in a syn fashion, okay? So if that's the case, then in theory, there's going to be some sort of cis-alkene intermediate species, right? With hydrogen and platinum metal, we can't isolate this cis-alkene intermediate, okay? So again, we potentially could want to, our cis-alkene, and again, we would get the cis-alkene because those hydrogens add in a syn fashion. We can't do that with hydrogen and platinum metal. Could we potentially want to do that, though? You guys don't know the answer to that question, but yes, potentially we could want to actually isolate this cis-alkene. So the question is, well, how do we do that? We can't do that with this hydrogen and platinum metal, with this catalytic reduction or this catalytic hydrogenation. So how are we going to go about isolating the cis-alkene? So we can't do that with hydrogen and platinum. We're going to do that instead with something called a Poison catalyst. So again, the purpose of this is taking alkyne and producing a cis-alkene, not fully reducing it to the alkane. So we can do that, except now the reagents are going to be hydrogen again, but we have to use a poison catalyst. And we have a couple of options for the poison catalyst. The first one is called Lindlar's catalyst, which is a bunch of stuff down here that you don't really have to be concerned with. The second one is called P2, which is a nickel boron complex. So there are two options here: hydrogen with Lindlar's catalyst or hydrogen with P2.
Why is it poison?
It's poison because it only reacts once. Like they do stuff to it so that it only reacts once. It doesn't react twice to get the alkane.
That's poison?
It's poisoning it.
So we just write a P2 or?
P2 would be, yeah. So you have options here: hydrogen and P2, or hydrogen and Lindlar's catalyst over the arrow. That'll take your alkyne and produce the cis-alkene. And again, it's going to be an internal alkyne that we're dealing with here. Okay, so we have a route to take an alkyne and produce an alkane. That's just going to be that normal hydrogen and platinum. We have a route to get our alkyne into a cis-alkene. That's going to be hydrogen with a poison catalyst. Now the question is, what about the other alkene? What would be the other alkene that we could potentially want to make from this? If it's not cis, then what would be the other version? Trans, right? So the question is, okay, well, how do we go about taking an alkyne and producing a trans-alkene? That's going to be another reaction, and that is something called a dissolving metal reduction. okay? So in this reaction, what we're gonna do is we're gonna take our internal alkyne. This is gonna be in the presence of sodium metal and liquid ammonia, okay? That will produce our transalkene, overall product. So we have our alkyne. This will produce our transalkene.
It's only 20%.
What?
It's only 80%.
Yeah, it's not a perfect reaction, but it will get us our transalkene. Okay, Wes, go ahead.
Sorry, this is called the dissolving metal reduction.
It's
the
called
other one?
dissolving metal reduction.
It's just the poison.
Poison catalyst is not dissolving metal.
You have to worry about the
Two
acid
different
and alkyne.
No. Okay, so I am going to go through the mechanism for this one. This is going to utilize radicals, right? So with radicals, we're dealing with one electron transfers at a time. So instead of using our normal double-headed arrow, we use a fishhook arrow to illustrate that. I'm not going to do that today, though. So we'll be done for today, but we'll start back here on Monday, and we'll go through the mechanism for this reaction.
3 weeks.
But then that's all we have to worry about with reduction of alkynes. There's 3 different reactions. Guess who comes after that?
Nothing.
Hydrohalogenation. We deal with hydration of alkynes. We deal with halogenation.
Oxymorph.
And then we're going to learn how to form carbon-carbon
Sounds like
bonds.
a lot of flashcard happening.
Yep. Yes.
Is that an I in the middle, is that iodine? Or what's?
Liquid.
NH? Oh, okay, in liquid form.
Liquid ammonia. Sodium metal and liquid ammonia.
So reduction is adding H's.
Reduction is adding H's.
Oxidation is that O3 thing that we learned in.
Ozonolysis. Did we learn O3? No, I didn't go over O3. No. That would be oxidation, yes.
Okay.
Ozonolysis. We'll talk about how you can determine the oxidation states of various carbons when we deal with alcohols. So we'll deal with oxidation reduction of alcohols. We'll learn how to determine oxidation states then. It'll be a little bit clearer.
Does it get really ugly after the show? You said it's gonna
Yeah, it gets bad. I mean, this is actually not that bad. It gets even worse.
Those words.
Way worse.
This is still like, oh, you can kind of use first principles to understand a lot of this. When we get into like things like Diels-Alder and pericyclic reactions, it's just like, okay, well. Aromaticity, Huckel's rule, it gets a lot of fun. So.